Okay, so I'm gonna start recording. I'll see. I might need to move this table or something around so I can get a better view. Okay, so I'm not going to go exactly in the order of my questions. I will give some physical motivation, and then we'll kind of do the questions roughly in the order that we go in. Okay. So let's see. I don't remember quite what the questions were, but okay. So let's start. We're going to talk about classical mechanics very, very roughly, and we're going to talk about classical mechanics. We're going to start off with a very simple system. We have a particle moving in one dimension. Okay, we have a particle moving in one dimension. Very good. So this can be many things, right? This can be, say a particle just kind of zooming around somewhere. Maybe I could have, say, a mass on a spring, right? And I can think of this mass on a particle, right? And then it would oscillate or do something. So that would be good. And okay, there's other examples that you could, in principle, come up with. Okay. So first of all, our goal will be something like this. What do we want to do in classical mechanics? For this case, yes.
Describe how it moves along time.
Yes. So ideally, I would be able to tell you. So I'll rephrase that slightly differently. That's the right idea. Is so goal. Goals will be in red. Goals. So the main goal is to predict the state of the system after some time t. Do you agree? So that's exactly the same as I want to figure out how's the thing going to move around in time. Do you agree? Okay. So we read this goal, and so clearly we need to understand what this means, right? I gave you a statement. We need to understand what the words mean. Okay, the word predict makes sense. The word the makes sense. The word state, does that make sense? Kind of, but actually maybe we should define what this is. Okay, what is a state? So the state of a system for a particle moving in one dimension. What does that mean? Or what should it mean, right? This is some physical words, right? I want to now come up with a mathematical model that will describe this physical system, right? I want to somehow formalize this. So let's formalize this. Yes. The coordinates of the object and what?
In the system.
Okay, good. So one thing, okay, the coordinates of the object. So suppose I tell you that the particle is here. Do you know everything about the state of the system? No. What else do you need?
Like where it's going and what direction it's going. Like the speed.
So yes, so you want to know where it is and the speed. These are the two things you want to know. So we define, for the particular case of the one-dimensional of a one-dimensional particle. So I give you a definition. The state, actually, this is working, right? Turned on. Oh, it is turned on. Oh wow, I didn't mess this up. Good. So the state of my system, well, of a 1D particle, of a 1D particle, is some point x comma p in R2. Do you agree? Where, kind of physically, x is the position of the particle, p is the momentum. So, great. The point is, suppose I knew the position and the speed of my particle at any time. Do you agree? Can I then figure out the acceleration? Right, because the acceleration is the change of velocity over time, right? So if I know the velocity at every point in time, then I can figure out the acceleration. Do you agree? That makes sense. Yes, question. Well, okay, yes. I need to give you something else in the about the system, but in principle, if I knew the position and the momentum of the particle, then that's the state of the particle. I know everything there is to know about that particle at that particular moment. So we realized that for a one-dimensional particle, so this is called the state space, or if you read Arnold ODEs, this is called the phase space. And I mean, in general, this is even called the phase space. So this is the, let's use maybe yellow. So this is the phase space is the space of states of the system. Okay. And so once again, you have to, everything I tell you, you have to think of this in the mindset of like, we have some physical system, and I come up with a model that describes this system, right? So here I'm just, I'm putting physics words into a mathematically rigorous picture, but the point is that, the system is not defined by this math. It's the exact way around. It's the math that I come up with is defined by how the world works, right? Yes, okay. The space of states, correct. And so now, I told you that the state of a 1D particle is this thing. So let's figure out how can so yeah, let's draw this, right? The state of space of a 1D particle in this case is a point xp and R2. Do you agree? R2 is, that's clear what that is. That's just a plane. Do you agree? So, for example, let's call this x and call this p. Have you guys seen axes like this drawn before, like x and no? Okay, maybe. Okay, that's fine. Usually people don't discuss this in high school. Okay, so for example, I have a particle in one dimension. Suppose the particle is here. Do you agree? Okay, suppose the origin is here, right? So if a particle is here in this region of my phase space, where is the particle on this picture and which way is it going? Yes, so it's somewhere here and it's going this way, right? If the particle was here, then let's say here, right? It's at the same x, but now going in the negative direction. Do you agree? If the particle was here, then it's where? It's left and to the right. Okay, good. Right, actually, yes. Actually, this is the problem. I want to ask for people's names, but I realize I'm recording, so maybe people don't want their names on the recording. So, yes, if you are willing to voluntarily share your name, and it might be on the recording, after you ask a question or answer, please say your name. I don't want to call on people and pressure you. Okay, so now we realize that a point in R2 actually can be, I can come up with this, and a point in R2 in these coordinates is going to tell me the state of my particle in 1D. Okay, very good. Now what do I want to do? So we figured out what this word means. Now we want to figure out how this state of a system evolves in time. Okay, so let's see how this will look like. I have a state of my system, right? Suppose I start here, right? And then what will the state do? It will change in time somehow for whatever reason. And how is it going to do this? Well, as the state changes in time, there's going to be, it's going to be at different times at different kind of points in the phase space. Do you agree? So what is it going to do? It's going to start here, and it's going to start and trace out some kind of curve. Do you agree? Which we can call, I don't know, x of t. Well, I guess not x of t, let's call it gamma of t equal to x of t comma p of t. Do you agree? So this will be a curve in phase space. Do you agree? So now we've rephrased this problem of predict the state of the system after some time t. We've rephrased it as we want to find some particular curve in R2. Do you agree? These two problems are equivalent in some sense. Okay. Yes. Okay. People agree with this reformulation. It's not too bad, right? Yes. Okay. So now what we have to do is we have to figure out. Okay. Well, how do we figure out this curve? Well, clearly we need some additional information about the actual system, right? Just knowing what the phase space is isn't enough, right? The system can have the same phase space but be doing different things. Like in this example before, I could have a free particle or I can have a mass on a spring. Those have the same phase space, but then the way they move in that phase space is different. Okay. So this is where I asked if people know the wonderful equation F equals ma. So, you know from Newtonian mechanics, this way. Right? So we know from Newtonian mechanics that somehow, right, the dynamics of a particle given via F equals ma. Do you agree? Okay. So these are the forces. This is the mass of the particle. A is the acceleration of the particle. Okay. Do you agree? However, our phase space is this x and p thing. Do you agree? So I want to rewrite this in terms of x and p. Yes? Okay, you guys always answer. I want someone else to answer. So first thing, what is A? What is the acceleration? You know this. We just talked about this. This is the acceleration, yes. What is that in terms of, maybe it's the derivative of what? This is just p, this is momentum. Okay, well, not quite. Acceleration is the derivative of velocity, right? So acceleration is the derivative of velocity. So it's d dt of v. So I'm assuming that people know what a derivative is. Okay, I'm not going to explain that. Okay, instead of writing d dt, because that's lame, I'm going to write v dot. Okay? Because, see, I have to write so many letters, and here I don't have to write so many letters. So it's much, much better. Okay? Now, so almost correct, but see, this is v and not p. However, you might know that, how is this related to p? Yes, so we know that p is equal to mv. Do you agree? So this means that ma is equal to mv dot is equal to just p dot. Do you agree? Okay, so in principle, this is not always true. This is what momentum is a separate discussion. But, as far as we're concerned, momentum is just mv for today. Okay? Okay, you can read Arnold's Mathematical Methods of Classical Mechanics, or you can read, if you know what a derivative is, you can read Landau and Lifshitz Mechanics. Great book. Yes, great book. Okay, so now let me rewrite F equals ma in terms of this thing. Okay? So I have F equals to P dot. Okay, very good. This we've made so much progress. However, we need, so yeah, F equals ma has become this. F equals P dot. Okay? And now what we have to do is we have to find x somewhere. Do you agree? So we have to, yeah. So how is x related to P? Is there any relation? So What is v dot? Oh, sorry, what is v? V is, yes, it's x dot, correct. Not what you said. Okay, v is x dot. So that means that p is equal to x dot, so mx dot, correct. Well, you assume that the mass of the particle is constant. And you can factor out a constant from a derivative, yes? Because the derivative is a linear map, as we all know. Right, so calculus is the study of a particular kind of linear map in a particular kind of space. So in fact, everything is 240, but that's okay. Well, actually, you know, that's not true because, okay, I'm not, it's funny, but it's not entirely true. Okay, so now we can rewrite, we have these two conditions. We have this condition and we have this condition. Okay? So we can now write these as a system of equations. What's the system of equations? P dot is equal to my force. My force can depend on where I am and how fast I'm going. So the force is in general a function of x and p. Do you agree? And then I have x dot is equal to p over m. Okay? Huh. That looks very interesting. Do you agree?
Yes.
That looks very, very interesting. So now we have to go back and interpret what this means in terms of my phase space. Do you agree? So my claim is, well, actually, I'm not going to make a claim. I'm going to have you make a claim. So I'm trying to find what? I'm trying to find x of t and p of t. Well, sorry, let me use orange for this. I'm trying to find gamma of t equal to x of t and p of t, which is going to be the trajectory of my system. And I know, trajectory of my system in phase space. And I know that these x and these p have to satisfy these two differential equations. So I have to find functions x and functions p such that they do this. Do you agree? Where in principle this f, so this f of x of t, comma p of t, because my force changes depending on where I am and maybe how fast I'm going at that particular moment in time. Do you agree? So suppose I drew this curve gamma in my phase space, okay? So suppose I knew what the solution was, right? How does this relate to this? Correct. So actually, I'm gonna do something you might not like. I'm gonna rewrite this and switch the order of the bottom one at the top. And yes.
Yeah, I was gonna say if you take the derivative of gamma t, then those are the coordinates of gamma t.
Exactly. So let me rewrite this. So I have x dot at the top because I just like x being at the top, and then p dot is equal to f as a function of x of t, p of t. Okay. So yeah, if I was to take the derivative gamma dot of this thing, if I took right, so if I computed gamma dot, right, gamma dot of t, that has to be precisely, well, x dot of t, comma p dot of t, right? Because I can kind of separately look at how each of the coordinates is changing, right, and have a derivative for each of the coordinates. But then what I can do is I can plot this on here as a tangent line to my graph. Do you agree? So this is the point gamma of t, and then this tangent vector is going to be gamma dot of t. Okay? Sorry that I'm kind of rewriting things all over the place. Do you agree with this? Okay. So now, well, let's look at this. So x dot equals to p over m, right? So this is P of t over m. Okay. So if I knew that I'm in some position of phase space, say here, do you agree? Suppose I knew that at some point in time, my position in phase space was this. Do you agree? From the first equation, I can figure out what the x component of my of this vector has to be, right? I know that if I was here at some point in time, that means at that point in time, the kind of vector should be precisely p over m. So the kind of x coordinate has to be p over m. So well, in this case, actually, it would be in the negative direction, right? So this should be p over m. And then suppose that my force only depends on x and p, which it, almost always does. Then if I knew that I'm here and the force depended this way on f of xtp, and f was a given function to us that we knew what the function is, then if I was at this point, I could always calculate what, or well, I don't know, maybe it's this way. I could always calculate what f of this point x comma p is. Do you agree? And if I knew the point, I could always figure out what the tangent vector should be to my curve. Okay? So in other words, so this system of equations, so these equations define a vector field. A vector field on the phase space so in other words, given these equations, I can at every point of my phase space draw some arrow. Okay? This is all that I mean. So at every point in phase space, I have an arrow that is attached. So so I will erase this diagram, but in your notes you should just draw a copy of this diagram. So, whatever the vector field is, at every point, I'll get some. At every point, I'm going to have some vector, and I'm going to know that, say, okay, whatever the vector is. Okay, whatever the vector is. And I'm going to know one thing. This is maybe not the best drawn vector field, but okay, we'll see what the point of all of this is in a moment, why I'm drawing this vector field. And I know that if I was to, that my trajectory, that my system will evolve in time according to this vector field. In what sense? My system's evolution in time will be some curve that is tangent to this vector field at any point in time. So my system. So these equations define a vector field. Let's call it x of p. Well, field x, x of I don't know, x of x comma p. And my system will evolve according to gamma of t, where the curve gamma of t is tangent to x of gamma of t at every t. Do you agree? So I'm going to stop and give people a moment to process this. Yes, question. What do you mean? Oh, a field in. So, a field in the sense of a field that you learned in Math 240 is completely different from a vector field or a field in physics. They're the same word used to mean something else. So don't confuse yourself with. There's two fields. There's R and there's C. Okay. Okay. Do people agree with this? And so now we've once again reformulated this problem. If now the question is, if I want to yes, if I want to, sorry, right, and sorry, let me, right, where x is, so in this case, x is what? X is a map from R2 to R2. Do you agree? X is a map from R2 to R2 because it takes in x comma p, it takes in two numbers and outputs some vector in R2 as well, right? Yes?
Why is gamma t tangent to x gamma t every t?
Because I said what? I said my trajectory in my phase space has to solve this equation. Do you agree?
Yeah.
Where x dot is equal to p of tm, and then p dot is equal to f of xt p of t. And so this vector field, sorry, I should have written a definition for it. I'm going to write a definition for it now. This vector field that this system defines, this is the vector field x of x comma p is equal to p over m f of x comma p. So this is the vector field, right? And gamma has to be always tangent to this vector field. Because, well, that's what f equals ma tells me. Do you agree with this? Yes.
Not gamma dot.
Well, gamma has to be tangent, meaning that gamma dot has to be equal to this. So the curve, the tangent vectors to the curve has to be these guys, meaning that gamma dot has to be precisely equal to this. And so in other words, okay, can I erase this other board? Or at least parts of this other board? Is this okay? Yes? So in other words, what we're trying to do, so now we've written the goal in a mathematical way, well, in a slightly more mathematical way, that we want to find gamma such that gamma dot of t is equal to x of gamma of t, where x is equal to, well, that. X is x of xp is equal to p over m, and then this is f of x comma p. Do you agree? Okay. So in some sense, we have transformed our physics problem into a geometry problem, right? You know, we realize that if you tell me what the physical system is, if you tell me, you know, if you tell me what the physical system is, and I know enough information about it, then I can figure, and I know what the forces are, right? If I know what the forces are, I can figure out what this vector field has to be. Do you agree? And then, so I have some vectors in my phase space. And so the goal of finding the trajectory of my system through the phase space, so how the state evolves in time, is just drawing a curve that is tangent to each of these vectors at every point in time. Okay?
Wouldn't this one be tangent to that one? I don't know.
Which one?
X of gamma t, if that one's equal to the derivative?
Yes. But the point is, I could draw many, many curves which can do whatever they want.
Yeah.
But the right one that is going to be the physical motion of my system is going to be the one that's tangent to all of these vectors.
So should not be blocked. What?
No, this is x evaluated at gamma of t. So gamma of t is some point in the phase space, and gamma dot has to be the vector at that point. So if my curve passes through this point, right? This point is what? Gamma of t naught. Then its tangent vector has to be x of gamma of t naught.
So not the opposite of what it says there.
The system will evolve according to gamma dot, where gamma dot is tangent to this. Or sorry, where the tangent, that's the well, actually, gamma dot is tangent to the vector. The vector is where gamma dot's tangent is. Okay, sure. Yeah, so the tangent, this is the tangent vector. Okay, potato, potato. Yes.
So do we flip it or don't flip it?
The vector has to be tangent to the curve.
Okay.
Whichever way makes.
What is the vector field on gamma or gamma dot?
The vector field is, you have a vector at every point. So it is, so I need to input a vector, and so I need to input x and p, and output goes a tangent vector. So you feed in gamma of t naught, because I have a vector field at a point. Okay, sorry. So the goal is now, if I know the physics, if I know the forces, I can draw this vector field. Do you agree? And then I just need to find a curve which is tangent to this vector field. And of course I need to be going at the right speeds along this curve, but okay, that's fine. Okay, so you see now this is a geometry problem. Okay? Now, one of the interesting cases and simple cases is when x is what? Well, x is a map from R2 to R2. Do you agree? It's a map from a vector space to a vector space. Oh wow, exciting. So in principle, x in some cases can be linear. It can be a linear map. Do you agree? And so one important class of systems is where this vector field, so important class of systems is what? Is where x of x comma p is linear, is a linear map. And this is what the first question, well actually what both questions talk about in the suggested exercises. And so, okay. Yeah. Okay. Pardon?
I thought taking a derivative.
Well, taking a derivative is linear, but it's linear on what space? It's linear on the space of functions.
Oh, I see.
Do you agree? But then, you know, what the actual slope is, that can be, you know, whatever from a physical system. Yes.
We are talking about tangent vectors, right? So
Yes.
we consider rotation by 90 degrees. Aren't rotations also linear vectors?
Yes.
That's the question.
Yeah, that's it. So yeah, sure. I could have a system where instead of, and actually this is a system that we will study. In fact, that is the harmonic oscillator. For the harmonic oscillator, this vector field is literally a rotation matrix. Okay, and we will. That's kind of why I drew it as a rotation, because we'll look at that later. Okay, but yeah, let's talk about it later. So first, okay, do people see this physical motivation for all of this? Okay, so now we're going to stop talking about physics for a little bit, and we're going to just study how can I solve this ODE where x is some linear map. Okay, and then we're going to. That's what the first exercise is about, and then we're going to go back and solve the harmonic oscillator as the second exercise. Okay? People agree with me? Okay. Because the solution of the it's like a little different. There's some there's some things to think about. Okay, but yeah, people now realize how we've gone kind of we've started off with we started off with this idea. I want to predict the state of the system after time t, right? I defined what the state of the system is. The state of a system is some point in R2 for a one-dimensional particle. And so finding the evolution of a system should be the same as figuring out what curve it traces in R2. F equals ma defines me some vector field, which the curve always has to be tangent to. So the goal is to write down. We know what if you know what the vector field. The goal is then to just find all the curves that are tangent to this vector field. Okay. And that's just what classical mechanics is in this case. Okay. Good. Yes, actually, let's do one simple example. One really simple example. Suppose I had a free particle. Suppose I had a free particle. If I have a free particle, what are the forces? So let's do green. Free particle. F of x and p is equal to what? No, just free particle with no anything. It's just a free particle in space. There's nothing. There's just a particle and there's nothing else in the world. Zero. Correct. Free particle. Okay. So let's write down what this vector field is, and then let's draw it. Okay. So the vector field at every point is x. So x of x comma p is what? It's p over m, and then what? Which is? Okay, thank you. Good. Actually, is this a linear map? Hell yeah, it is a linear map. So this is the matrix acting on xp, where x gets sent. So x gets sent to 0, and p gets sent to 1 over m0. Okay. So in this case, x is a linear map. This is, yes, correct. Do you agree? So in fact, this is already in this important class of systems. Maybe this is a completely trivial system, but okay, stop complaining. So let's draw this vector field. We should draw this vector field to just get a hang of it. Okay, so what do? I have to, at every point, I have to draw a vector. Do you agree? And the vector that I have to draw is this one. Okay. So at 0, what's the vector? 0. Okay, right? Right. If I have my particles at the origin and it has 0 speeds, it's going to stay at 0 speed. Yes.
Isn't the kernel not just space? Like
the kernel. This is not an invertible matrix. So the kernel is not the empty. Yes. In fact, you can see that x is in the kernel. Okay. Good. So now suppose my particle was at 0, but with some momentum, p. Positive momentum, right? The vector is going to be what? P over m going which way? No. To the right, correct. So this is p over m, do you agree? Suppose I looked at, same p over m, but at some other point x. What is the vector here? It's the same vector. Right? Because just look at the equations. P over m in the x coordinate, 0 in the y coordinate. So this has to be a horizontal vector. And so in fact, if I was to draw this, I will realize that if I'm staying kind of on the same p coordinate, then the vector is always the same length, regardless of where I am at x. And then it gets smaller as I kind of it gets progressively smaller and smaller. and then it becomes just 0 at 0, right? If my particle, okay, and then it switches sign after I go through the, after I go through this, through the origin, right? Why is this, of course this is how it is, right? Why is that? Well, if I have a free particle, we know from Newton's first law that if I throw a ball, it's just going to keep going straight with the same speed. Do you agree? So this means that if I am staying, if I start at, say, this speed, right, my speed isn't going to change, so the curve has to be horizontal, right? Because I can't have any change in momentum, so the curve has to be horizontal. And if I have a speed to the right, then my position is going to be changing to the right. So, you know, the tangent curve to this is just going to be a straight line this way. Okay. And now the important part is you have to figure out the parametrization of this curve. So how does this, how fast am I going along this curve, right? So in phase space, I figure out what the trajectory in phase space is, but I also need to figure out how fast I have to go along this trajectory. Okay, but that's kind of the additional information in the differential equation. Okay, so if I have a free particle that starts off here and then moves with speed in the negative direction, then okay, the trajectory is going to go this way. Okay. Do people understand this simple example? Yes. What? In the beginning, when it's up there. Yeah. When it's up there? Yeah. Well, P over M. Yeah. Here, this coordinate's X, this coordinate is P. Oh, wait, P is positive. So it's this direction. Okay. Correct. Okay? Good. So we see that, you know, this system that we've done makes sense with this kind of simple case. And we see that in the simplest case possible, this X is in fact a linear map. So it makes sense to study, in general, how to solve this kind of thing. Okay. In fact, I'll write everything down for a two-dimensional example, but we will figure out how to solve this in n dimensions. Okay. Well, I'll write down the answer, and then you'll just believe me, because how can I lie? Okay. Can I erase all of these ideas? Okay. So now we're going to kind of, you know, kind of abstract away a little bit, but maybe still remember the motivation and study the problem of solving a linear ODE. So, new problem. Solve a linear ordinary differential equation. Okay. So what am I going to be given? I'm given a matrix. So I'm given a matrix A. So this is some n by n matrix. And I want to find... Oh, well, wait, sorry. This, I don't want just a... Is it just a matrix, or is this a... Yes, matrix. And I want to find gamma of t, which is going to be a function from R into Rn, such that gamma dot of t is equal to A applied to gamma of t. Okay, so this is called an ordinary an ordinary linear differential equation. Do you agree? So gamma of t at every time in t is an n-dimensional vector, so I can apply a matrix to it. And then if I can take a derivative with respect to kind of each coordinate, and that's also an n-dimensional vector, so okay, I can search for a curve gamma of t such that this is true. Do you agree? Given some matrix A. And we've realized that in classical mechanics, for a one-dimensional particle, this is roughly what we have to do. If we had a particle that moved in 3 dimensions, then okay, this would be a more dimensional map. So okay, this will roughly, this is what we're getting at. Okay, people agree. This is what I want to solve. So let's, does anyone actually have the suggested exercises open? So we're going to solve an example to figure out what the overall idea should be. And then, what kind of the idea is. And then we're just gonna write down the answer, and then I'm gonna like not prove anything about it, but it's gonna be so believable that you're just gonna believe me. It's gonna be so true, like it's gonna be obviously true. Yes. So can someone give me the suggested? Beautiful. Okay, so we're going to try and solve the following thing. So we're going to look at an example. Crazy, me giving an example. Ooh, rough. Okay. We're not actually going to solve the example. I'm just going to kind of say the answer, but like we're going to roughly solve it. So the thing we want to solve is x dot equals to, what is it, 3x minus y?
3x plus y.
Oh, it's over. 3x plus y. Oh, I remember why I picked this example. Okay, this is a great example. Because this example is solved in like one of the questions, roughly. Oh, so then oh no, but is it skill issue? Yeah, it's skill issue. That's fine. And so I want kind of x of 0, y of 0 to be, well, I want it to be some, okay, x naught, y naught. Okay, so I want to solve this ODE, right? I want to solve this ODE subject to these initial conditions. So that at time 0 I'm at this point, and then I have something. So let's, okay. Do you agree? So this is some linear system, and so I can write this as some as a matrix, right? So this should be what? This should be x dot y dot equals some matrix applied to xy. What is this matrix? Can people tell me what this matrix is? 3, 1, 1, 3. Okay, beautiful. That's correct. Great matrix. Okay, now I'm gonna like cheat just to make sure I don't forget. Okay. Okay, this. Okay. Okay, good. But this looks a little difficult to solve. And actually, first, before we solve anything, we should figure out what we know how to solve to begin with, right? So what do we actually, does anyone know what we actually know how to solve? If you read the question, you would know. But there's only one thing that we know how to solve. And that one thing is? What's the one thing we know how to solve? We know how to solve one equation and one equation only. Or at least I know how to solve one equation and one equation. Maybe you guys know more than me. But the only equation I know how to solve is y dot is equal to ky. Subject to the initial condition, y of 0 is equal to, I don't know, to c. And I only know how to solve this in one dimension, where y is a function from r to r. Do people know what the solution to this is? Yes. Correct. So in fact, if you want to solve this in one dimension, then y is equal to c times e to the kt. Okay, this is the only thing I know how to do. Do you guys know what the exponential function is? Okay, it does this. its derivative is equal to k times itself.
Yeah.
Okay, that's all I said.
Oh.
Right? So in fact, one way to define the exponential function as the unique solution to this equation. You can believe me that it is unique. So y dot is equal to ky, y of t, so this is the solution, and this is all I know how to do. All I know. And remember, this is a one-dimensional problem. Do you agree? This is somehow a two-dimensional problem. And that's kind of hard. Okay? So let's maybe, before we tackle this problem immediately, let's tackle a slightly different problem. Slightly easier problem. So that I am not overwhelmed. Because I am easily overwhelmed, as we know, by all of these complicated things. So let's look at a very simple problem. Suppose I had x dot y, so this is what we want to solve in a moment. Suppose I went to solve x dot y dot is equal to lambda 1, 0, 0, lambda 2, xy. Okay. Do we know how to solve this? Right? Because what is this? This is really x dot y dot is equal to what? Lambda 1x and lambda 2y. Okay. See, I have x dot equals to lambda 1x and y dot equals to lambda 2y. Do I know how to solve this? Yes, because I've kind of managed to separate out my my basis so that I kind of have an equation for one variable and then a separate equation for another variable, right? And so then the solution to this would be just e to the lambda 1t times x naught, and then y naught e to the lambda 2t. Do you agree? So somehow, if I was able to write my matrix in a diagonal way, I know how to solve everything. But do you agree? So what do I want to do? I want to get a diagonal matrix. Do you agree? So I want to turn this into a diagonal matrix, which is actually not always possible. In this case, I chose a nice matrix such that it is. Okay? But how do I get a matrix to be diagonal? I have to do a change of basis. So if I did a change of basis, I could find what some linear combination of x and y has to be as functions. And if I know what some linear combination of x and y has to be, then I can figure out what x and y have to be. Do you agree? So now, I'm going to tell you that we're going to look at the following basis. Okay, so do people get the idea here?
What's the last thing that you wrote?
So I'm telling you that the solution to this equation is just the one-dimensional solution for each thing, because here I can kind of separate out, in the diagonal matrix case, I can kind of separate everything out. Yes. Even if the matrix wasn't diagonal but was like upper triangular, then I can still do it. Well, hopefully. Well, I won't talk about that. I'm already saying many things, and we still have a lot to cover and not much time. But I don't care, I'll just keep talking. What are you going to do, leave? Oh yeah, you can leave, I don't care. Yeah, you can literally just leave.
Question.
Yes?
Can we go overtime in this?
Pardon?
Can we go overtime in this?
Yeah, I will keep talking until I don't want to talk anymore, and then if I don't want to talk anymore, I'll leave. Or if I don't want to talk myself, but I'm willing to listen to you say something, I might stay. Like I'll do whatever I want to do. Okay, so we want to do a change of basis. Okay, suppose there was a change of basis. Let's call it, what's a good letter for a change of basis? Lambda. So suppose there was a lambda which is invertible, such that I had what? Such that A, I do say lambda this way, and then I do say lambda inverse here, was equal to D, where D is a diagonal matrix. Okay, suppose I had this. Do you agree? Okay, then okay, I can kind of multiply by okay. So oh wait, sorry, this is A. This is A. So this implies that what? A is equal to lambda D lambda inverse. Okay? Do people agree with this? I just multiplied by lambda on the left. This became the identity. Here I got a lambda, multiplied by lambda inverse on this side, and okay, got it. Good? People agree with this? Okay. So let's rewrite this equation in terms of this and see if we can simplify it somehow. So I can do what? I can do, so I have x dot. So okay, instead of gamma, I'm writing, well, I don't know. Let's keep writing gamma. Gamma dot is equal to A of gamma. Actually, I should start writing this in like a green color or something. So this is like a new idea kind of something. So gamma dot is equal to A of gamma. This is the equation we originally had. So now let's write this as, let's substitute this, D lambda inverse gamma, okay? So I have gamma dot is equal to lambda D lambda inverse gamma, okay? So what can I do now? I can kind of apply lambda inverse from here to this other side. Do you agree? So I can get lambda inverse applied to gamma dot is equal to D applied to lambda inverse of gamma. Do you agree with me? So all I did is this is a matrix. I moved it to the other side, and good. But actually, you know, what is lambda minus 1 inverse applied to gamma dot? That's just me applying some taking some linear combinations of derivatives. Do you agree? So at most, I'm adding things and multiplying them by a number, a fixed number that doesn't change with time. So in that case, in fact, this guy should be equal to the time derivative of the whole thing. So kind of ddt of the whole thing. So the derivative should commute with this transformation. Why? Because lambda itself is some fixed matrix. It doesn't depend on time. So I'm just taking some linear combinations. That should commute with my derivatives. Do you agree? Okay. But now let's call this some kind of new vector, you know, x tilde, whatever. Do you agree? So now I have what? I have, this is the key big step, x dot is equal to dx, where D is a diagonal matrix. Right? Right? And so now, so D is diagonal, meaning that D is some lambda 1, lambda 2, okay, up to lambda n. And then zeros on the diagonal.
Wait, that's x tilde, right?
Oh yeah, x tilde dot x, yeah, sure. Do you agree? This I can solve very, very easily. Do you agree with me?
Yeah.
So this, x tilde, this is what? Can someone tell me what the solution is by analogy to last time? It's, so x, yeah, so x1 times e to the lambda 1t. So this is kind of x01. This is x02 e to the lambda 2t. Okay, dot, dot, dot. you agree? So I know the solution to this explicitly. And of x0 n e to the lambda n t. Do you agree? Okay. But if x solves this equation, right? I can work backwards and realize that if x solves this equation, that this gamma solves the original equation. So I found what x has to be. So this means that gamma is equal, so gamma of t is equal to what? Is equal to what in terms of x? So it was like this, and so gamma is equal to lambda x, correct. Yes. And there is no other x here anyway, so, well, not really. Okay. So this is one approach. This approach assumes that there is some matrix which diagonalizes my A. This is not always true. Not every matrix can be diagonalized. Okay? But in general, this is pretty good.
Wait, that came from there, right? Like, that came from that.
What came from it?
The last step came from.
So it came from this.
Which came from that? Like,
yes. So I said, suppose I can rewrite my matrix as like if suppose there existed a lambda such that if I do this to A, this is diagonal.
Yeah.
Right? So then I just rewrite my equation in terms of this, right? Then I can rewrite this equation further like this and realize that, okay, this is just some new vector x tilde. But it's very easy to solve for x tilde because d is diagonal. But then I defined x tilde to be some fixed matrix times gamma, so I can figure out what gamma has to be. Okay? Very good. And so now, okay, you can do this. You can do this for this system. And how can you do this for this system? So you roughly need to find the eigenvectors of this matrix, whatever that means. So eigenvector. So remember, change of basis is like doing something like this is roughly like doing a change of basis. A change of basis means I just go to some different coordinates. Do you agree? So essentially, I'm trying to find coordinates such that the first vector just gets scaled and the second vector just gets scaled. So in some sense, I'm trying to find vectors which are, by this matrix, are just scaled. So in some sense, I'm trying to find the eigenvalues and eigenvectors of the matrix. Whatever that means, you don't know yet. But soon you'll see, and that's okay. For this matrix, how you're supposed to find the eigenvalues and eigenvectors, it's because in problem something of the warm-up, you were given this matrix and you were told what the diagonal, you were essentially told what this has to be. And let me try and guess what it is in front of you. And so maybe we'll fail, maybe we won't. I'm running out of space. I shouldn't. Okay, I just want to keep this here so we have reference. So I will erase this and rewrite. Instead of this, I'll just write this in the corner here. Okay, so so we're trying to solve x dot y dot. So trying to solve x dot y dot is equal to what was it? 3, 1, 1, 3? X, y. Okay. So now I'm just gonna guess what lambda is, and you're gonna like low-key trust me. And well, we'll multiply it out and check that it's the right lambda. So it should be. What did I have here? I had a is equal to this. So this lambda has to be going from the diagonal basis. Good. So lambda should be 1, 1, and 1 minus 1. I think this is correct. Okay. Now, this is a great question that you asked me, is we want to find the inverse of this matrix, right? And then we want to compute what D is. Do you agree? So, okay, let's do that very, very quickly. So this is a bit of computation, but this is not the most efficient way to do all of these computations. There's more efficient methods, but this is what we know. So okay, we compute the inverse by doing what? Okay, 1, 1, 1 minus 1. Okay, this is 1, 0. Whoops. Okay. So okay, I want to turn this into the diagonal matrix. What should I do? I should subtract the first row from the... Okay, I'll give you a moment to copy. I should subtract the first row from the second row, right? Oh, yeah, okay, let's add them first, sure. So 2, or, well, which one? Okay, let's add the bottom row to the first row. Sure, let's add the bottom row to the first row. So I have 2, 0. 1 minus 1. So this is going to be 1, 1, 0, 1. Okay, good. So then I have, then I want to divide the first row by 2. So 1, 0, 1 minus 1. Divide the first row by 2. 1 half, 1 half, 0, 1. Okay, then I want to subtract the first row from the second row to get 1, 0, 0 minus 1. So this is 1 half, 1 half, minus a half, 1 half. And then I want to multiply the second row by minus 1. So this is going to be, okay, I can just factor out the 1 half. This is going to be 1, 1, 1, minus 1. Oh, haha, it's the same matrix. That's crazy. Almost like I chose this to be brain dead simple to compute. Okay, so that's that. And so we just computed that lambda inverse is equal to 1 half 1, 1, 1 minus 1. Very nice. So here, like the point is here, I'm just kind of telling you what lambda is. In principle, you would need to figure out what lambda is based on what A is. But okay, this is something you will learn a little bit later in the course. Here, I'm just kind of telling you what the answer is. Okay, now we have to figure out what D is. Do you agree? Sorry, I'm erasing this very quickly, but now let's figure out what D is. So D has to be, so lambda inverse A lambda. Pardon? The top one? Yeah. I just told you that's the right lambda to use. I just told you that's the right lambda. So once again, later in the course you will learn how to find lambda on your own. Given A, you'll be able to find lambda. But right now, I'm just telling you this is it, and you would know this is it because you would have done the change of basis question in the whatever part and realized, oh, this matrix is the same as that change of basis question matrix. So just from having done it and having accidentally found the right answer, you would know the right answer. Okay, but there is a methodology to it. Okay, I don't care. So this is 1 half. Let's just multiply all of these matrices out. 1, 1, 1 minus 1. This is 3, 1, 1, 3, 1, 1, 1 minus 1. Okay, let's maybe compute these two first. So this is 1 half, 3, 4, 1, 3, 4, 3, this is a minus, right? 3 minus 1, 2, 1 minus 3 minus 2. Okay, and then I still have to do 1, 1, 1 minus 1. So yes, these are all of these matrices you would have seen in the warm-up question. So you would know. You would just know. You just know what the answer is. Yeah, this is true. Like if whenever you can solve a problem by just knowing down and writing down the answer, that's the best way to solve a problem, just by being better. Okay, 4 plus 4 is 8. 4 minus 4 is 0. Crazy. Okay. 2 minus 2 is 0. Oh wow, this is really a diagonal matrix. So I didn't mess up. 2 minus 2, this is 4. And so the eigenvalues are 4, 0, 0, 2. Okay, someone has to check that that's true. Yes.
If you didn't know if it's true or not, could you verify this by running into a problem later on in the problem?
Pardon?
Like if this weren't true, or if you got some other value, would you run into a problem later on that's like a dead giveaway?
Not necessarily. Well,
like possible situation like, oh, I probably computed this wrong. Go back and
that really depends on the problem and what exactly you're doing. Yeah, like maybe. Sorry. Okay. So okay. I will now erase this again. Like people just like this is just matrix multiplication. Hopefully you can do matrix multiplication by now. Okay. So I figured out what D is, right? Now remember the process. We rewrote our differential equation in a different basis, where D was acting on this x twiddle, and we figured out that in this diagonal basis, x twiddle, so it's equal to lambda inverse applied to gamma, and then if x twiddle dot solves dx twiddle, then that's equivalent to gamma dot is equal to a gamma. So if I find x twiddle that solves this, then I know that gamma dot defined from this will solve that. Okay, and so I can write down for our case, x twiddle has to be what? So it has to be x naught y naught times what? Yes, e to the 4t and e to the 2t. Beautiful. Okay? Well, actually, sorry. These are the initial conditions for x twiddle and y, I guess, yeah. x01 twiddle and x02 twiddle. Okay? And so we'll figure this out in a moment. Okay, and then, but I didn't want to find x twiddle, I wanted to find gamma. But what is gamma if not? Gamma is just what? In terms of x twiddle. Lambda x twiddle. Good. So, in this case, okay, let's go back to the computing corner. So, I want to, lambda is one, what? Lambda is one minus 1, and I want to apply this to x0 e to the 4t, well, x0 twiddle 1, x0 2 twiddle e to the 2t. Okay, and I do matrix multiplication. What else can I do? That's all the question asks. Okay, so this is x01 twiddle e to the 4t plus x02 twiddle e to the 2t, and at the bottom I get minus. So x01 e to the 4t minus x02 twiddles e to the 2t. Okay, this is messy. Now I write down the solution carefully here. I just rewrite the same thing. So gamma of t is equal to, there is no half because the lambda didn't have a half, right? Okay. It's the lambda inverse had a half, but the lambda didn't have a half, so we're good. My knee hurts. Okay, that you didn't maybe need to know. E to the 4t plus e to the 2t e to the 4t Okay, do you agree? And then if I want gamma of t to satisfy the right initial condition, then I just have to figure out the right x01, x02, such that at t equals 0, it fits the right condition. Do you agree? And so otherwise we're done. And that actually would be the same. So finding the right conditions would be this, because at t equals 0, e to the 0 is 1. So then I'd just be searching for x01, x02, x01 minus x02 is equal to the right vector. So that would just be applying lambda inverse to your initial condition. So actually, I'll just write this out explicitly. So gamma 01, gamma 02, sorry, I want to do it the other way. X01, x02, twiddle, twiddle. So the initial conditions are going to be which matrix going from where to where. So the initial condition, yeah, is just going to be lambda inverse applied to gamma 01, gamma 02. Okay. So you can figure out what the initial conditions for the x's have to be from the initial conditions for the gammas in a straightforward way. Okay. So this is the x0, that's the initial condition for this differential equation. This is the initial, gamma naught is the initial condition for this equation. So what does my gamma have to be at time 0? What does my x have to be at time 0? No, whoops, this was not showing. Okay, well, no one's going to watch this video anyway. It's going to be like a 2-hour-long video. I upload these and they all have like 2 views. Each 50 seconds long, but it's okay. Like there was one video of a guy presenting from my reading group, and that video for some reason got like 200 views. I have no idea why. I'll send you a link. Yes, you guys should make friends with each other, and so that you can send each other the things I sent to some of you individually. Like, because some people ask me for things and I send it to them, but then I don't particularly care about the other people. Well, not that I don't care, it's just that I don't remember. Well, there exists, there already exists a Discord server. It's just that you're not in it, Don't worry. There already exists a Discord server for my reading groups, but okay. Maybe you don't need to know about that yet. Okay. So now in principle, if you knew how to find this lambda matrix, for some matrix A, you know that, okay, you know how to solve all of these ODEs now, in principle. You have an algorithm. Problem is, not every matrix is diagonalizable. And we'll see that in a moment. That's the harmonic oscillator. It's not quite diagonalizable. That sucks. That's one thing. The other thing is, not every matrix is diagonalizable. And end of that's it. There's nothing else I have to tell you. However, there's actually a theorem that says there's always a solution gamma of t for any initial condition if A is a matrix. And so we want to write down the answer. Well, once again, we want to just write down the answer without all that much thinking. Okay, so if you have to go, you can just wait for me to write down the answer. Well, surely the answer is kind of the same always. Do you agree? So, and here I have the answer, right? Do you agree? So in some sense, like, see here, the matrix was diagonal, right? So what did I write? I wrote that the answer is just, okay, I have e to the whatever for each of the matrices. But, in some sense, what I almost want to do, so I'll erase this part. Hopefully people wrote this down. Okay. Somehow what I want to do is write down something like this. What I almost want to do, I almost want to say that gamma of t should be, well, I just want to write down the same thing and like not think too hard. I almost want to say that gamma of t should be E to the matrix A times T applied to my initial condition. Right? That's I want to write this down. Because in this case, that was true, right? In the one-dimensional case, the solution was E to the eigenvalue times C, because this is a one-dimensional matrix, right? And we realized that actually, if A was diagonal, if I had A was diagonal, then in some sense the solution, right, was really E to the lambda 1t, E to the lambda nt applied to the initial condition. In some sense, this was already the case for a diagonal matrix, right? And if it worked for a diagonal matrix, surely we can do something like this. Okay. So the question is, what is this? Right? I have to define this somehow. I want to write this down, but what does this mean? You agree? Okay. And so I tell you what it is. I'll just tell you. Right? So we saw that this is the answer if A was diagonal, but maybe if A is not diagonal, maybe I can still write down something similar. And in fact, so here's where I define definition. I define the matrix exponential. So the exponent of some matrix A is equal to infinite sum from n equals 0 to infinity of A to the n divided by n factorial. Where A to the n, I mean compose the matrix with itself n times. And A to the 0 is the identity. So where A to the 0 is equal to the identity. Do you agree? So this is some infinite sum of my matrix. Okay. From Math 157, you're going to look at this, and the first thing you're going to ask me is what? Yes. Well, no, it's too far. First thing is like, is this even well defined, right? Oh, whoops, I'm running out of battery. So the first thing you're going to ask me, does this converge, right? I gave you some infinite sum and said that this infinite sum means something. But it better converge, right? Hopefully. The answer is, well, it does converge, trust me. I'm not going to prove that it converges, but because that requires me to add, introduce more concepts, and we're already over time. But let's kind of roughly see how, if I assume that this converges, and I assumed a bunch of other things, how this would be the solution to this. Okay? So I will now erase this. Yeah, if you need to go, that's fine. Okay, but the idea is, so with a harmonic oscillator, we're going to write down some matrix. It's still going to be a linear equation. X of p is going to be a matrix applied to x and p. The problem is that matrix, it was going to be a rotation by 90 degrees clockwise, and so that cannot be diagonalized because rotations don't have they don't stretch any particular direction. But it turns out that if you look at a basis with complex coefficients, for some reason you allow complex numbers to enter the scene, then you can diagonalize the matrix, and you do, and then you can do the process that I just erased, and then write down your answer, and it's going to be sine and cos. But okay, that's further. Yes.
So there's some process that turns this into the thing we talked about.
Yeah, or alternatively, if you just wrote down the rotation matrix and computed what this infinite sum converges to, then you would get explicitly the solution.
Is it always the same computation, or will it change?
I mean, depending on the matrix, you'd compute the sum differently because different matrices work slightly differently. So, this is kind of a, okay. So let's, so claim, yeah, I'll try and post this video, so hopefully you won't miss out on all of that much. Ooh, this is tough now. I made a... Okay, I'm gonna move you. Yeah, you're being moved. Sorry. Yeah, see ya. Yeah. Okay, hold on. Let me just. Okay, sure. Sure.
Okay, like basically during like the little
Mhm.
talking section,
Oh yeah.
yes, they kept asking me like what grade I got,
Oh, I see. I
and I
see.
said high 90s, but now I don't want to like scare them off.
I mean, just don't just.
We would just say.
Okay, can you ask me after? Like, send me an email
You'll
about
send
it.
it.
Yeah. Okay. Yes. Okay. Also, mention to them. I mean, I'll do it myself. You should mention fall campus day to them. Okay. Don't worry about it. Okay.
I can send that in my email.
Yeah. We'll. Don't worry about that. Yes. Exactly. Yes. Correct. Oh, be careful. Yeah. Okay. Amazing. Okay. Thank you. So, let's try and finish this up very quickly. Okay. Let's prove. So the claim is that this solves this with some initial condition. So I want to do what? I want to do. So let's define gamma of t equals exp at applied to gamma naught, where gamma naught is kind of the initial condition vector. Okay, this is what? Good. So at t equals 0, right? Right. So this exp of t is still going to be a matrix, so it makes sense to apply it to gamma naught. So let's write down what this really is. So let's compute ddt of gamma t. Okay. This is ddt applied to what? Applied to. Okay. Let's do this sum. A to the at to the n divided by n factorial applied to gamma naught. Okay. Now, I will commute the derivative and the sum. This is, you can't always do this, but it turns out that this converges very nicely. So in fact, you can do it because it converges very nicely. But I do not want to prove that this indeed converges, so I won't do it. And so this is roughly a to the n times, times a scalar t to the n divided by n factorial. Do you agree? Times applied to gamma naught. Okay, and if I take the derivative of t to the n, so I need to do ddt of this, right? This is just some matrix multiplied by some scalar, right? So some fixed number, we're taking a derivative with respect to this fixed number. Do you agree? So I can just, I should just be able to just take the derivative of the number because the matrix is a constant, right? So, because roughly, like, you can think of it as I'm doing it in every component, and every component, the stuff that comes from a to the n doesn't depend on time, but then only t depends on time, so I can just take a derivative of t to the n with respect to n. What do I get? I get t n minus 1 times n. Do you agree? So I just took the derivative with respect to time. Very good. So now I can write what? I can rewrite this as infinity n equals 0 of a to the n t to the n minus 1 divided by n minus 1 factorial applied to gamma naught. Do you agree? Okay. And the actually, I can start the summation from n equals 1. Why? Because the n equals 0 term was just the identity matrix. And so the derivative of that with time is just 0 because it doesn't depend on time. Do you agree? So, okay. Now I can factor out an a. Do you agree? Because everything is a to the n, I can just factor out a matrix a. And I get a times this infinite sum. And now I can start the sum at 0. And I'll just have at to the n divided by n factorial applied to gamma naught. Do you agree? Okay. But what is this? So I shifted indices by 1 down, right? I shifted indices and factored out an a and got this, right? factor out an a, got an n minus 1 here, then everything here is n minus 1, so I can shift an index to start at 0, and then it's all the same. Okay, but what is this? This is precisely our solution, gamma of t. So this is a applied to gamma of t. Okay, so if you were able to prove that this thing converges, and it converges nicely enough that I can commute the derivative with the sum, then you see that this is indeed the solution. Okay, and you can check that if you plug in t equals 0, then all the terms go to 0 except for the 0th term, which is the identity, and so I get gamma at 0 equals to identity times gamma of 0, which is just gamma of 0. Okay, very good. So we've found a general way to solve anything. Any linear differential equation. Okay. I think I should probably stop now, but I will outline very roughly as to what the harmonic oscillator is, and then you can figure out the rest. Because these are suggested exercises. I'm not supposed to solve the exercises for you. Okay. The harmonic oscillator has what equation? The harmonic oscillator has f equals to negative kx. Correct. So let's set k equals to 1 for simplicity. Yeah, just set k equals to 1 and m equals to 1 for simplicity. Do you agree? I have what? X dot equals to p over m, and p dot is equal to f of xp. Okay, but this means that what? This means that in this case, x dot is equal to just p, and p dot is equal to just minus x. Do you agree with these coefficients? Okay. So this means that I want to solve gamma dot is equal to 0, 1, minus 1, 0 applied to gamma. This is the equation I want to solve. To solve the harmonic oscillator with k equals 1, m equals 1, I need to solve this. Okay. This is a rotation matrix. It's a rotation by 90 degrees this way. Okay. So clearly, there is no basis in which it is diagonal, right? Because if it was in some basis it was diagonal, that means there exist some vectors which just get stretched by this matrix. But rotations don't stretch any vectors; it just rotates. So clearly, this doesn't have any whatever. So in your question, in the way you do it in suggested exercises, so I won't write anything else down. But in the suggested exercises, there's like 3 ways of doing this. One way is the way of suggested exercises, where we still do the procedure before with finding a basis in which it's diagonal. But I just told you there is no basis in which it's diagonal. So how do you do that? You allow a vector, your vector, to have complex numbers. And if you allow for complex numbers, then your calculations in the process are complex. But when you kind of change the basis back to gamma from the x twiddle, you get something that's real, and you get that x is a linear combination of cos plus sine, and then cos plus sine. But how do you get cos and sine? The idea is that if you have e to the I phi, then that is cos phi plus I sine phi. Right? So you allow for complex numbers. You get that the matrix is diagonal, but the stuff on the diagonal is a complex number. And so you get that the solution is e to the I something complex, e to the something complex t, and then e to the something complex t. And then once you change bases back, you get that the kind of the sine phi parts cancel out, and you're just left with some cosine or sine in whichever way you get it. That's one way. Alternatively, what you could do is you could figure out how to exponentiate this matrix. So what the nth of these, what the nth power of these matrices is, and then you can figure out that actually you'll get that it's right. Because what does this do? This flips rows and then multiplies the second row by -1. Right. This is what it does each time. So you could kind of separate this into the even and odd bits. And then you can figure out what the sum is for the even bit, what the sum is for the odd bit. In each case, you will find out that it's a diagonal matrix in some sense, and you will And so then if you knew what the Taylor series is for cosine and sine, then you could immediately sum this and find the solution to the harmonic oscillator's cosine and sine from that way. And then the third way to do it is the geometric way to do it, which is what Arnold talks about. And the third way is to literally like, this is some vector field, right? I can draw this on my phase space. If I draw it on my phase space, okay, and then I'll stop. This is becoming very long. If I draw this on my phase space, so I'm drawing x of xp is equal to p minus x. Do you agree? Okay. So suppose I'm at this point. This vector, so I'm at this point. This vector is going to go which way? So it's going to be pointing this way and then a little down, right? Because positive x, that means I get minus here and then it's in the y coordinate, so it's down. But one thing you can realize is that this vector has to be perpendicular to x comma p, just by computing the dot product, right? If two vectors, you take the dot product, you get 0, that means that they're perpendicular to each other. Do you agree? And xp dot p minus x, of course, has to be 0 because I get xp minus px, which is 0. Do you agree? So I know that this vector has to always be perpendicular to the radius vector, and it also always has to have the same magnitude as the radius vector. Okay? So if I look at this carefully, whoops, I'll realize that the vector field is this kind of circular one. Do you agree? And also this vector field is rotationally so I always have to be tangent to the radius vector. From this you can kind of you can say some words, make an argument that my trajectory has to kind of stay on the circle. My trajectories have to be circular in phase space. Okay. Whatever. My trajectories have to be circular in phase space, and because there is like a rotational symmetry to this problem, then I know that as I go along this space, the speed with which I go has to be constant. So from this you can conclude that gamma of t has to be some, cos t plus some phase sine t plus some phase. Just because I want to be going around the circle with constant speed, so it has to be cos t sine t, because that's the coordinates on my circle. And then, okay, maybe there'll be some prefactor with actually, I think this is correct for the case k equals 1, m equals 1. And if you wanted to solve for k not equal to 1, m not equal to 1, you can always rescale. You can always choose different units of length and time, such that in those units you get that k equals 1 and m equals 1. Solve it in these coordinates, and then unscale your coordinates where the problem is simpler. So roughly, you can always do like a scaling of whatever matrix you get, so that this matrix becomes a -1, 1 matrix. Solve in those coordinates, use this solution, and then scale back. Okay, but yeah, sorry. This is really what I would have liked to talk about, this very nice geometry that you get a circle in phase space. And that's why, so you have like cos and t. Cos and sine are something about triangles, right? Well, okay, the triangle is, this one that tells you where you are on this unit circle. Okay, but yeah, we're actually exactly 2 hours, which is exactly how much I wanted to talk. But it's 2 hours starting, 30 minutes after when no one asks me any questions. But yeah, I'll stop recording and then I'll post this.